Hello, this is Mr. Gilmore with the 8.2 Part 1, the Pythagorean Theorem and its converse. Oh, what a frabjous day, Kalu Kalay. Today we finally get to do it, folks. We get to prove the Pythagorean Theorem. Yes, we've been waiting for this moment for a long time, and we have everything we need now to dive into the depths of our proof. So let's start by introducing what is the Pythagorean theorem. Well, you guys may know it as the a squared plus b squared equals c squared, but above is our conditional, and this is what it states. If a triangle is right, then the sum of the squares of its legs equals the square of its hypotenuse. So down below we have triangle ABC with the sides labeled lowercase a opposite of capital A, lowercase b opposite capital B, and lowercase c opposite capital C. And so what we've found here then is we have our so-called Pythagorean theorem, a squared plus b squared is equal to c squared, where we are going to square each leg, add them together, and then it will be equal to the square of the hypotenuse. Now here's what our proof is going to look like today. First what we're going to do is we're going to drop an altitude to the hypotenuse. This is from our very first lesson in 8.1. And what we found then, and this is moving into step 2, what we found was that there are some special theorems that we can then pull out of the right triangle when we drop the altitude to the hypotenuse. So we're going to use a theorem from our previous lesson, 8.1, and we're going to write out a pair of proportions. Then what we're going to do is we're going to cross multiply those proportions. We're going to algebraically massage those proportions together, and then pop, there goes the Pythagorean theorem. It just out of nowhere, kind of like it's always been sitting there the whole time, waiting for us to prove it. And there it will be as we reach the conclusion of our Pythagorean theorem. So which theorem from 8.1? We're specifically going to be using the geometric mean leg theorem, or to us, the GMLT. Now what this one says, it says that each leg is the geometric mean of the whole of the hypotenuse and the piece of the hypotenuse adjacent to that leg. In other words, if you take a look through the two proportions below, each of these two proportions do one of two things. First, they both involve the hypotenuse, AB, and that's a key component because we're going to relate, right, the legs of the right triangle to the hypotenuse. The next thing we see is that in each proportion that we have each leg being used, and that's the geometric mean, right? AC is a leg, BC is a leg. Now we're going to see that these last two little pieces, AM and BM, well, what do we know about them? They are both the parts of the hypotenuse. I wonder what happens if you add those two parts together. It will equal the whole part of the hypotenuse. So we're going to use all these components here then to bring to life the Pythagorean theorem. All right, so let's play. This is the proof of the Pythagorean theorem. Before we dive into the two column, let's look above at our diagram and what we're given and what we are asked to prove. So in the diagram, you'll notice a few things have been added to our diagram. It's still the same triangle ABC, only this time we have constructed that altitude from our vertex of our right angle to the hypotenuse, which means we do have that altitude to the hypotenuse. So just like back in 8.1 when we did that, we found a bunch of similarity, and using that similarity, we found the geometric mean theorems. And again, we're going to be using that GMLT here in just a moment. Now you'll also notice that where the altitude intersects the hypotenuse, there's a point here, though I don't have it labeled because I don't really need it labeled. But what you've seen there is that I have labeled a few segments. So there's the segment from point A to where the altitude intersects the hypotenuse. I've labeled that as a length of x. And then there's the segment y, which is from point B to the point of intersection of the altitude again. And you'll notice then that we're going to be relating, right, these 5 variables together. We have the two legs, A and B. We have the hypotenuse C, and we have the two parts of the hypotenuse, X and Y. And we'll use those two pieces here in a little bit as we dive into our proof. One quick thing I do want to point out before we get into the proof is that if you take a look at what X and Y are, those are both pieces of the whole hypotenuse. If I took X and added it to Y, it would equal C, the entire length of the hypotenuse. So just keep that in mind, that X plus Y is equal to C. All right, so we're given again that triangle ABC is right with right angle C, and we're trying to prove that a squared plus b squared equals c squared. So where do we start? We actually start with similarity. We know that these triangles are similar, so using the geometric mean leg theorem that we've proven, we bring to life two proportions. So take a look at step 2. In step 2, right, we see that we have the proportion set up of the hypotenuse to the leg is equal to the leg to the piece adjacent to it. So we have C over A, and I've chosen A to be the first leg, right? So C over A equals A over Y, because as you see, A and Y are adjacent. Then for the second proportion, I use the GMLT again to get C over B is equal to B over X, because again, X is then adjacent to the side B. Now, when we had back in chapter 7, we proved that with proportions, we are allowed to cross multiply. Now, we didn't have a name for that theorem, so I just simply called it the 7.1a theorem. So what I'm doing from step 2 to step 3 is simply cross multiplying. So a times a is a squared, c times y is cy, b times b is b squared, and then c times x is cx. So what we're going to then do is take those two equations, which we know to be true, and add equals to equals. So using the addition property, we do a squared plus b squared. So we get one of that with that left-hand expression that we're looking for, a plus b squared. But on the right hand, we get cx plus cy. So now we have to then do something with that cx plus cy. Notice then going from step 4 to step 5, that if those two terms on the right-hand side both have a c value in them, let's factor the c value out. That's using the distributive property. So we take the c out, and what we're left with in this expression of c times x plus y. We'll go back to that thought we had earlier about what's going on in our diagram. X plus y equals c. So then with segment addition postulate and some substitution, we take x plus y out, replace it with a c value, and c times c is then simplified to c squared. That all gets wrapped up into substitution. And there we have it, folks. Step 6, a squared plus b squared is equal to c squared. We have the Pythagorean theorem. Hurrah! And it's all thanks to several theorems that we established way back in chapter 7 with the proportions and our similarity leading us into the geometric mean leg theorem. And with those theorems in place, it is very simple for us then to prove the Pythagorean theorem. So let's actually use the Pythagorean theorem in an example. So given a right triangle with legs of length 7 and 24, what is the length of its hypotenuse? Well, we can draw a picture of this if you wish to. We're given a right triangle with the two legs, 7 and 24, and we're looking for the length of hypotenuse, which means when we apply a squared plus b squared is equal to c squared, we are then using 7 and 24 as our a and b values. Now, it doesn't matter which one I call a or which one I call b, so I can call this one a, I can call this one b, and then let's plug in our respective numbers. So I'm doing 7 squared plus 24 squared, and then solving for what c squared is. So evaluating, 7 squared is 49, 24 squared is 576. Let's add 49 and 576 together. We get 625, and then we can take the square root of both sides. When I do that, I get a c value of 25, and there we have it, using the Pythagorean theorem to find a missing side. And so on the worksheet, you'll be actually using the Pythagorean theorem in the same sense of now not just proving it, but actually using it in application and finding missing side measures of a right triangle. Now, as it turns out, the Pythagorean theorem has a true converse. We like to call this simply the Pythagorean converse. Let's see what this states. The converse of the Pythagorean theorem says that if the sum of the squares of two sides of a triangle equals the square of its third, then that triangle is right. Now, notice that we didn't use the vocabulary of legs and hypotenuse, and that's simply because we can only use that vocabulary when we're speaking about a right triangle. Well, we don't know that this triangle is right. What we're going to prove is that the triangle is right. In other words, we're going to show that one of its angles must be a right angle. So here's our setup for the Pythagorean converse. If what we're given is we're given triangle ABC such that the length of A is less than or equal to C, and the length of B is less than or equal to C. In other words, we're using this to say that C is the greatest of the three values. Okay, so we want to make sure that C is the greatest of the three values in the order in which we're plugging them into our given equation, which is we know it to be true that a squared plus b squared equals c squared. So we know that to be true. What we're trying to prove in this case then is that triangle ABC is right. In other words, what we're going to show is that our angle C is a right angle. That's what we're going to show. If we can prove angle C is a right angle, then we have ourselves a right triangle. Now, we start off with a strategic construction. So what we're going to do is we're going to use our ruler postulate and our protractor postulate. So let's start first by using our protractor postulate. With our protractor postulate, we may construct a right angle. So I've constructed angle T as a right angle. Then with the ruler postulate, I'm allowed to measure and make measure. So I'm going to measure side A and duplicate it so it becomes side R. I'm going to measure side S measure side B and duplicate it so it becomes the side of S. And then I'm going to simply connect R to S, thus forming a right triangle, and label our hypotenuse as T. So that's where we have this second triangle from. I'm simply just using the power of constructions that we have with the ruler postulate and the protractor postulate to bring RST to life. Now, what we're going to then do with this construction is we are going to arrive to our conclusion that triangle ABC is also going to be a right triangle. So now let's dive in to the proof. So we have our two triangles again, triangle ABC, triangle RST. Now we know that triangle RST is already right, which we'll take advantage of that here in a second. And we know there's already a relationship built between the two triangles, saying that A is equal to R and B is equal to S. So we're given, again, this is the converse, so we're given A squared plus B squared equals C squared. We're going to prove that angle C is a right angle. So where do we begin? Well, let's take a look at our given. Our given is simple. We have A squared plus B squared equals C squared, and we know that A is equal to R and B is equal to S. So what I'm going to do is in my first equation there with A squared and B squared, I'm going to take the A value out and replace it with its respective equal counterpart R. Do the same thing for B. Take B out and replace it with its equal counterpart S. So now what we have going from step 1 to step 2 is a new equation. We have R squared plus S squared is equal to C squared, and that's just simply by substitution. But we already know that triangle RST is a right triangle. So take a look at step 3. It's a really important step. If triangle RST is already a right triangle, then the Pythagorean theorem is true. R squared plus S squared is equal to T squared. Now, using step 2 and step 3 together, take a look what's happening with this R squared plus S squared. They both add up to C squared and T squared, which means we know by transitivity of equality, C squared is equal to T squared. Using our square root property of mathematics, we take the square root of both sides, we simplify, and we get C is equal to T. What is that saying now? What that says is that the three sides of one triangle are equal to three sides of another. So congruence steps in. Yes, the power of congruence. And we know that triangle ABC is now congruent to triangle RST by side, side, side congruence. Then with our good pal CPCTC, we know that the measure of angle C is equal to the measure of angle T. Well, if T is given to us as a right angle, right, we constructed T such that it is a right angle, and C is equal to it, that means whatever is true about angle T is also true about angle C. So if angle T is a right angle C must also be a right angle. And there we have it with the power substitution. We know that triangle ABC must be a right triangle because we've proven that it has a right angle in it. And so there we have it, the converse of the Pythagorean theorem. Now, we give the Pythagorean converse another title. We like to call it the right triangle test. So what this really says then is that the converse of the Pythagorean theorem really tests to see if a triangle is a right triangle. How do we know? It has to satisfy this equation. So what we're going to do is we're going to take the three sides given to us and plug them in such that C is the greater of the three values. So we will have to plug C in here, right? This is going to be the greatest value that we have of the given three values, and when we plug them in there, if it satisfies the equation and we say yes, then yes, that's a right triangle. But if the equation is not satisfied, which means the equation is false, then we do not have a right triangle. Let's actually use this right triangle test in a few examples. So a triangle has side lengths 5, 12, and 14. Is it right? Well, let's test this. We have then our A and B and C value. Now notice that I let my C value be the largest value. It needs to be the greatest. So now let's plug these into the equation. A squared plus B squared is equal to C squared. And really it's more of a question. Is A squared plus B squared equal to C squared? So we have 5 squared plus 12 squared. Is it equal to 14 squared? Well, we get 196 on the right-hand side with 25 squared, or sorry, 5 squared is 25, 12 squared is 144. Add those together, we get 169. Those are not the same. So is that triangle a right triangle? No, it does not satisfy that equation, that equation A squared plus B squared equals C squared, which means we do not have a right triangle. Let's test our next example. Another triangle has side lengths of 9, 12, and 15. Is it right? Well, again, we need to let the C value be the greatest value, and then we can plug in our A, B, and C values respectively. So I have 9 squared plus 12 squared is really question, is it equal to 15 squared? Well, let's simplify. 15 squared is 225, 12 squared is 144, 9 squared is 81. Add 81 and 144 together, we get 225. So yes, this is a right triangle. Yes. So using the Pythagorean converse, that right triangle test, we know we can test to see if triangles are right or not based on their three sides. So we've come to the end of our lesson 8.2 part 1. You'll see we'll continue into the next lesson 8.2 part 2 with carrying over the Pythagorean theorem and some other information with it. If you do have any questions on the 8.2 part 1 worksheet, be sure to email me and I'll get back to you. With that, be good and do good.